First off, if you remember for discrete variables, we had what was called a PMF, a probability mass function. That was a probability distribution for a discrete random variable. For continuous, we call it a PDF. You don't need to know the difference between the two of them. I'm not going to test you on that. It's not a huge deal. Just an FYI that we call a probability distribution something slightly different depending on if it's a continuous or a discrete random variable. So in theory, and again, I'm not going to test you on this, but in theory, I should be able to say I have a PDF or I have a PMF, and that right alone would tell you if it's discrete or continuous. But we're not going to dive down that rabbit hole. This is just an FYI for the terminology. The key part of this definition that I want you to catch is that it is thought of as a curve that would be attained from smoothing a histogram obtained from infinite sampling. There's a lot of words in there that might throw you off. Focus in on this idea that if we were to take a histogram, which we had defined previously, it's a bar graph for numbers. And if we had this bar graph of numbers, but instead of having thick bars, we made the bars really, really, really thin, um, so thin that they were, paper thin, and then we just had basically all the heights of those um, bars as our probabilities, and we took those as those heights and just made a curve. That's what a PDF is. And so in chapter 4a, when we talked about discrete variables in general, we always had a table to work with. In chapter 4b, we said if we have a binomial variable, we um, have the opportunity to find the probability, find the f of x via this formula. That was the nice thing about identifying a variable as binomial. Now with continuous, again, now we're in a whole different world. Now we're driving on the other side of the street here with continuous. We won't have a table and we won't have a formula. Instead, what we'll have is a curve. Okay, so it's like we had talked about when we first defined a probability distribution. It's that it says what are all the values of x and what are all the probabilities. Well, let's stop and think. With discrete variables, it makes sense that you could make a table because if it's discrete, that means there's gaps. That means I could list out all my possible x's and then I can list out a probability with it. But if you think about that for a continuous variable does not have gaps, meaning that 2.5 is possible, 2.65 is possible, 2.655 is possible, 2.78219 is possible. So imagine trying to list out all of these possible x's knowing that there's no end to the decimals, right? So you can quickly see how that's impossible to do. So the idea of having a table um, goes out the window. So instead of tables with continuous variables, we often will talk about curves. Now the formula idea still holds true as well. We're not going to focus on that in this course. There is a formula for the normal curve, um, but it gets complicated. We're not going to dive down that rabbit hole. There's formulas for other um, types of continuous variables, kind of like we had with the binomial. Not something we're going to focus in on though. We're just going to be focusing in on the curves here. So some properties. Um, First off, a probability distribution for a continuous random variable is f of x, just like in discrete, but f of x represents the height of the curve and not a probability. Okay, so this is one of the key differences that we need to make sure we understand between discrete variables and continuous is that both of them have probability distributions and we label them as f of x, but in a continuous case, f of x just tells me the height of the curve. Okay, think about back in algebra when you saw an equation y equals 5x plus 2, something like that, and sometimes you might have seen that as f of x equals 5x plus 2. F of x was y, it was just the height of the curve, so that should make sense to you there. It is not a probability. So in a discrete variable, um, f of x is a probability, and a continuous f of x, not a probability. Why is that? Because in a continuous situation, the probability that x equals any number is always 0. Why is that? Let's just think through a quick example. If I were to say that there were 20 people in a room and I wanted to know the probability that I randomly selected any one of those people, you can probably quickly figure out that my probability would be 1 out of 20 or 0.05. Um, if I were to take that same room and now I were interested in the probability of picking a person out of now 200 people, let's say I've created it from 20 to 200, my probability now goes to 1 out of 200. If I were to keep doing that, I would end up with 1 out of 2,000, 20,000, 200,000, 2 million, etc. And I would eventually get up to, if I have an infinite number of options, 1 divided by infinity would be 0. And you say, no, wait a minute, where did the infinite number of options come from? Remember, we're in continuous land here for continuous random variables, and if there are no gaps in my possible options, there are an infinite number of possibilities that x could be. This is the idea with saying a variable like weight is continuous, right? A person could be 160 pounds. They could be 160.01 pounds. It could be 160.0001 pounds. It could be 160.000000852 pounds, right? There's an infinite number of options we can come up with. And so the probability we randomly select one of those numbers is 1 divided by infinity, how many different options we have, which is 0. So f of x is not a probability in a continuous random variable like it is in discrete, because there is no way to ever land exactly on a number if I have an infinite number of options. And so you say, well, great, I don't know what to do with that then, because previously our work in chapter 4 revolved around writing a probability statement, potentially rewriting it if needed into a series of probability x equals something, and then replacing that with f of x. And that was accurate. That was how we worked with chapter 4. Chapter 5 and 6 moving forward with continuous, we can't do that, right? We cannot rewrite a probability statement as a bunch of probability x equals somethings and then replace those with f of x's, because f of x is not a probability, and even if it were, those probabilities are all 0. So what do we do? Okay, instead, we're going to be focused on area under the curve. Okay, so we would take a situation like probability x less than a is just any number. That's the area under the curve to the left of a. So instead of focusing on probability x equals something, we're going to think about what about it being less than something, because I can't say what's the probability that I pick a person in the classroom and their weight is exactly 160 pounds, because no one in the classroom weighs exactly 160 pounds. They might weigh close, but they actually weigh 159.99982 or 160.002, right? No one weighs exactly that much. Now, side note, do we have the measuring devices to measure to that depth? Probably not, readily available, but they exist, right? That's the idea, is that if we had the devices to measure someone to that precision, no one weighs exactly 160 pounds, so we can't do that. But we could say, what's the probability that I pick someone and they weigh less than 160 pounds? That actually is possible, right? Because then I would say, yeah, there's a ton of people in there that are going to weigh less than, someone who weighs 150, 155, 140, 120, etc. Whatever, right? There's going to be a handful of people who do. And I could go the other direction. I can say, what's the probability that someone weighs more than 160? And there would be people there too. So in continuous, we're always talking about probabilities that are greater than a number or less than a number, but never exactly equal to a number, because the equal to part isn't interesting because it can't exist. The probability is 0, but it's an impossible event. Or our third option would be maybe not just to the left or to the right, but in between. And that would be, say, what's the probability I pick someone and they randomly weigh between 140 and 180 pounds, right? And again, there would be people who would fall in that range. There'd be people outside of that range, people inside of that range. And then the last property here is to note that when we were dealing with discrete probability, we said the sum of all of the individual probabilities must add up to 1. It's a little bit different here, right? Because the sum of all the probabilities here is 0. Why is that? Because all of the probabilities are 0, right? The probability that we randomly pick someone and get that exactly, if we have a continuous distribution, is 0. So I add up a bunch of zeros, I get zeros. So the sum of the probabilities are not 0 in this case. Rather, because we're talking about area under the curve, we say the total area under the curve equals 1. Make sure you catch the total area under the curve is not less than 1, just because you see the word under there. What we're saying is the area under the curve is probability, right? And so the total probability has to equal 1 because the total area under the curve equals 1. And that's your key idea, is that probability and area are synonymous.